So this is an experiment to demonstrate or even measure resistance and how Ohm's law applies to very basic circuits where you have a voltage and there's a current carried by a resistor. So the components of the experiment are in front of you here. This is what you would see if you were in a physics lab actually with your hands on it. There's a power supply. It gets electricity from the main, which is in this case standard 110 volt AC. And then it converts that to DC, and the DC voltage is available at these two terminals. When this is on, we can change the voltage and we'll be able to see the voltage and the current flowing here. We have a separate meter which we can use to measure voltage or current, and the meter is currently off, but you can set this knob at whatever function you want to use this meter for, and then we plug wires into these connectors to get that function. So if we wanted to measure voltage, we'd have one wire here and one there, and those two wires would connect to the source of the voltage that we want to measure. If we wanted to measure current actually would flow through the meter, so this would become part of the circuit. And depending on what range of current we want to measure, we'd use either that connector or that one in combination with the common one there. This is a holder for wire, so that we'll be able to change the wire and measure the properties of that wire by applying a voltage to one end and the other. And various wires that we'll try are these that are part of a wire kit just for this experiment. I'll just hold this up here so you can see. There's a copper wire with a diameter of 0.04, an aluminum wire with the same 0.04 diameter. That's in inches now, so it's sort of a contradiction to the way we normally do this in this class. These are English units. Brass wire, 0.02, and then there's a brass wire, 0.032, and a brass wire, 0.040, and a brass wire, 0.050, and a nichrome wire, a really interesting material that's used for heaters, with a diameter of 0.040, and a stainless steel wire with a diameter of 0.040. So those are various wires. We can measure their resistance directly by putting them in this device. We're going to do that today as part of this experiment. And then behind that, over here to your right, is a variable resistor called a rheostat. And let's just look at that just for a moment. So it's got a wire coil on it, which goes all the way across. And depending on where we put the slider, we can make contact with that coil at various positions. So if we put a voltage from one end to the other, because the voltage varies uniformly through that resistor, we can pick off a variable voltage at this point, or if you like, going from here to here and then out there is a variable resistance depending on where we put this. So we're going to use this also as part of this experiment. So here are the wires up close. You can see 4 different kinds of brass. You can tell the brass from the color. So these are in diameter from the largest to the smallest here. The wire here on the far left is nichrome, which is a wire that's used to make heaters. It has a little more resistance than steel. It's still quite strong. Here on the far right is copper. You can see the coppery color. It's a little different from the golden color of brass. And then the wire next to it is aluminum. So these are the ones that we're going to make measurements on today. We know the diameters. These are standard English measurement diameters, but we don't know the resistance. Now we're ready to measure a piece of stainless steel wire, the last wire of the set. The other ones that you saw before we'll measure in a few moments. The wire is clamped here and here with 2 little screw-down clamps, And we can touch the wire with these metal bars here and here, which are attached to wires which go to a meter that will allow us to measure the voltage from this point to that point. So the wire is here. The wire itself is connected to a power supply that is delivering 1 amp to the wire. We'll come back and see how we control that in a moment. So 1 amp flowing through this wire. We touch the wire at 2 places and measure the voltage using these 2 connections, which go to a voltmeter. And this is the voltage in volts between that point and that point when there's a current of 1 amp flowing. I can move this point. This one's at 0, and right now this one is at 24, so we're looking at 24 centimeters on this wire, and the voltage drop for a current of 1 amp is 0.237. I'm just going to slide it along. We'll make a measurement at different positions, and then from that look at how the resistance depends on length. So let me just reach over. Better do it from the other side and move this slider from 24 to 22. And so we've got 217 now at 20, 199 at 18, 178 at 16, 158 at 14, 140 at 12, 118 at 10, 100 at 8, 080 and at 6, 059 and at 4, 040. It's nearly linear. So let's go back up to 24 again and just check that, which is 238. So this is in volts. There's a decimal point right there, so it's actually 0.238 or 238 millivolts across the wire, carrying a current of 1 amp. Now to get that 1 amp, we've taken 17.8 volts. That's what comes out of here. We're running that through this rheostat so that actually we apply that voltage between here and here. Let's see, well, actually, let me go back. Between here and here to get that voltage across the wire. So the path of that 1 amp is from here on this wire, which goes to there, through this one that we're measuring, out on this side, into the top of this rheostat, out on the back side over here, to there. And the purpose of the rheostat here is to get that current at 1 amp. The resistance on this is so low that if we just put any reasonable voltage on it, like 12 volts, the current would be really, really high. So we put a resistance in series with it to limit that current. This is a 20 ohm rheostat, and we're using about 3/4 of it to limit the current so that we can get something we can measure here. So we're measuring the voltage drop for a given current across that wire. We just changed right now. What we've done is to just change the position for the same current. Now we can keep the position constant. The full 24 centimeters is as good as any, and change the current. So that's the voltage for 1 amp. And I will reduce the voltage by reducing the supply voltage over here. And we'll just try some different settings. There's 0.87 amps, and we have 0.207 volts. .75 amps and 0.178 volts. 0.64 amps and 0.153 volts. 0.52 amps and 0.124 volts measured from here to here on this wire, which is carrying that current. This voltage, which is what we're applying to make all this work, doesn't have any role in this other than setting the scale. So I can change, and actually am changing that voltage, but the purpose is to change this current. This current creates the voltage that we're measuring here. So let's go down some more. 0.52, we'll go down to 0.42, and then it's 0.101 volts. 0.31, 0.074 volts. And 0.25, 0.060 volts. The errors get significant if we go much below that. So I'll come back up, set the output voltage back up to 18 volts where it was before. The current should be 1 amp. And for that 1 amp of current, 0.237 volts on this wire, which is clamped and measured at these two positions. So I'm going to change the wire. Now, so you can see how it's done in this one example. This is the wire I think is nichrome, and I'm going to stick it in under that like that, and then over here, and thread it up through there like that. Clamp it by tightening that nut and that nut. And then I'll move this test position over to 0 here, and this one over to 24 there. So we're just back to where we were before. Turn on the power and turn up the voltage. I'm looking for 1 amp of current. Just do it slowly. Now we have 1 amp again, and the voltage drop across this wire is now 0.315 volts, or 315 or 16 millivolts between those 2 points. All we've done is change the wire, but it's altered the voltage drop because the resistance of this wire is different from the resistance of the one we had before. So I'm going to repeat this for the different wires, and we'll just measure it wire by wire and look at how their properties vary. Now I've put the copper wire in, and I've set these 2 contact points at 0 and 24 again. And I'm going to turn on the power supply, which is all the way down right now. And then run the current up until we have 1 amp. Now you might think something is wrong. We're not getting a very big number here, but what does that mean? The reason that number is small is that the resistance of that copper is very low. So we now have 0.85 amps. And here's 1 amp, and we have only 4 millivolts. We might get a better measurement if I change the scale. So that's the 200 millivolt scale. Now we can see the voltage drop is 5.1 millivolts from here to here with a current of 1 amp flowing. It's hard to get it exactly 1 amp, but that's pretty close. Flowing in that copper wire. Let's see what the brass wires do. Now I've inserted the largest of the brass wires, and remember we had a little help guide on this. Tells us that the largest brass wire is 050 inches in diameter. And let's turn the power on here. I've set the scale again to 2 volts, and I'm going to come up with the current until we get to 1 amp. You see the voltage is coming up higher now than it did before with copper. So brass has more resistance than copper. And we'll work our way up to exactly 1 amp here. And it's 0.012 or 013 volts. Go to the millivolt scale and we see that it's 13.4 or 13.3 millivolts. That's the largest diameter brass, the 050 brass. The copper that we had in there before was 040. A little bigger diameter brass and than the copper, but the resistance is higher. So let's try it again now with the next size down in brass and see what we get. So this is 040 brass, and we're going to turn the power on. Run the current up to 1 amp. This is the millivolt scale, so this is 8.5 millivolts at 0.42. So we have 1 amp, 20.4 millivolts, and the brass in there is the 040 brass. So we have an 032 brass, which we'll put in next. So now we have the 032 brass, and I'm going to turn the power on. Again, on the millivolt scale, 200 millivolts full scale. This is amperes. This is the current which is going through that wire. And we'll increase that current. One amp, 33.2 millivolts between here and here. That's 24 centimeters apart on this piece of brass wire, which is 032, that is 0.032 inches in diameter. So we have another piece of brass we can put in, it's even smaller. So the brass wire which is in here now is the smallest sample that we have, and it's 020, that is 20 thousandths of an inch in diameter. I'll turn the power on, and we'll run the current up. This is in millivolts. So we're at half an amp now, and we have 42 millivolts. So we have, trim this up just a bit, 1 amp. To get that 1 amp, we have 17.7 volts going through this rheostat, but the voltage drop between 0 and 24 centimeters is 87.8 millivolts on this scale. So this is set to millivolts so we can see this better. If I set it to volts, you'll see it's 0.87, but by going to the millivolt scale, I can get another decimal point. It looks a little more reasonable. So now we've done all the brass wires that we have. We've done well, everything except an aluminum wire. So I'm going to put the aluminum in. Let's see what its resistance is. And we have an aluminum wire clamped from here to here, and we're sampling the resistance by measuring the voltage drop between 0, where this probe is, and 24 centimeters over here where the other probe is. These two wires connect to our voltmeter, and we're going to measure the voltage. It's now set on the millivolt scale when we run current through it by increasing this current so that it's 1 amp. So power's on, and we'll start the supply some voltage, and we see the resistance developing a voltage across that wire. We're at 0.38 amps, 0.4, just about a half an amp. Here we are at 0.70 amps, and then we'll get up to 1 amp. We have 16.1 millivolts between here and here with the aluminum wire. Aluminum has a relatively low resistance. Remember, when we put in stainless steel or nichrome, the voltage was much higher. We actually had to use the volt scale instead of the millivolt scale. Now, without changing anything else, I've put the original wire that we did tests on back in the holder so that we could look at how it compares to aluminum again, and I'll just turn the power on and we'll start to increase the current. So now we have 1/10 of an amp, 2/10 of an amp, 3/10 of an amp, 4/10, 0.50 amps, and we have 119.8 millivolts between 0 and 24 centimeters on that original stainless steel wire. We're up to 6/10 of an amp and 141.7. 7/10, 0.70 amperes, 166.3, or maybe 167 millivolts, depending. It's up to 0.8, 189.3 millivolts, up to 0.9, and we're off scale, so I'll go up to the 2 volt scale, and we see we have 214 millivolts, or 0.214 volts. And then we'll go up to 1 amp. And we have 0.237 volts. So this wire has much higher resistance than the other wires that we tried. The resistance depends on the temperature of the wire, but we're not drawing enough current to change that significantly. The wire is actually cool to touch for me right now. So let's just review what we've done here. We have a power supply. Right now, with this setting, it's delivering 17.9 volts between these two terminals. This voltage is carried by these wires, and we can follow them through pretty easily. So this wire, is that one right there, comes up to here, goes to that clamp. This is a wire coil, and we're picking off at a place over here where we've used about 3/4 of the length of this coil. This coil has 20 ohms from end to end, so this coil has a resistance in series with this voltage, and that limits the current. The current coming out of this goes through this wire, flows through this clamp to the end of that wire, which we're going to test, goes through this wire, comes out on this side where it's picked off again at this clamp, goes to this wire, which if you follow it around goes back to the other connector on our power supply. That current is the current which is flowing in this circuit and going through this wire. Then we measure the voltage that's dropped across that wire by putting a probe in contact with the wire here and there. These probes are actually just pieces of copper that are spring-loaded, so they press down on the top of that wire and make a good physical contact with the wire. So we can measure the voltage at this point relative to the voltage at that point. And we see right now it's 0.238 volts for 1 amp. So we've tried different positions to show you how the voltage depends on the length, and therefore the resistance of this wire determines the voltage drop as a function of length. We've tried different materials, each of different diameters, and we've tried different currents. So all the variables, materials, their size, the current and the voltage have been explored here. And all of this behavior can be explained by the sort of empirical law called Ohm's Law and the properties of materials that determine its resistivity.